Good morning, welcome to new lecture. Today I will review several exam problems. First problem, we have one rigid plate, and this rigid plate is hanging using 3 rods. And it is symmetrical system. So we have 3 rods, we have one rigid plate. The shape of plate, you see it is triangle. This plate is rigid, so let's say write rigid plate. And here E to A, young modulus is E, cross-sectional area it is 2A. The middle one, young modulus it is E, cross-sectional area it is A. First rod, young modulus it is E, and cross-sectional area it is 2A. Length for middle rod it is 2L, and for these two it is 3L. And this system is subjected to one concentrated load P at middle, you see, and this length it is again 2L. So we have one rigid plate and is hanging from ceiling, you see, using 3 cord or 3 rods. Each rod, young modulus, it is E, cross-sectional area is A, 2A, 2A. The length for middle one, it is 2L. For these two, it is 3L. And you see, this is symmetrical system. So, if I pull down here, I apply load P, this rigid plate will transfer down. So, the deformation in the rod 1, if I put it rod 1, 2, 3, these deformation they will be equal. So delta 1 will be equal to delta 2, it will be equal to delta 3. And this rigid plate only will transfer down and will move down. There is no rotation. This means if I assume each one as one spring, stiffness of the rod 1, K1, it will be E. You know stiffness, axial stiffness, it is EA over L. So for this one it will be E times 2L divided by 3L. So it will be 2EA divided by 3L. The stiffness for rod number 2, it will be E, young modulus, times cross-sectional area for this rod, divided by length for this rod. And K3 will be, again, 2EA divided by 3L. And because if I assume these rods as a spring with equivalent stiffness, I can calculate the stiffness. Now, because the deformation of each one is delta, or deformation for all are equal, so I attach these rods in parallel. So these rods, they are parallel. So the equivalent stiffness will be summation of K1 plus K2 plus K3. So I should add these 3K. So springs in parallel because deformation they are equal. From here I can find the total stiffness. Total stiffness will be 2EA over 3L plus 2EA over 3L plus EA over 2L. From here, this will be 6L 4EA plus 4EA plus 3EA. This will be equivalent stiffness for this system. So total deformation delta will be total force P divided by total stiffness or equivalent stiffness. So deformation delta will be P divided by, this will be 8, this will be 11 EA over 6L, or I can write 6PL over 11 EA. Now, I find deformation for how much this rigid plate will transfer down or will move down. Now, what is the internal force in each spring? Now here, F1, force in this rod will be stiffness of that one, K1, times delta K1 is equal to 2EA over 3L times delta, it is 6PL over 11 EA. And you see EA and EA, they will cancel out, L and L, they will cancel out. So this will be 12P divided by 33. If I want to find internal force in rod 2, again I will do similar thing. F2 is K2 times delta, and F3 is equal to K3 times delta. This is first problem. Let's look at the second problem. Second problem, I have one rigid link, something like this. This link is rigid. I attach this link to two supports using 4 rods. EA, EA. From here to here it is 2A. Each side is lowercase a. And we have top support and again 2 other rods, and EA, and this height it is A. This system is subjected to concentrated load P here. I want to find delta. Delta means I want to find how much this rigid link will move down. And you see here the deformation in these 2 rods. If it is delta, in these 2 rods should be delta in vertical direction. So deformation, because it is symmetrical system, deformation in all links, all rods in vertical direction, it is equal. So if I put, this is rod number 1, 2, 3, 4. If I apply P here, because this is rigid link, there is no deformation for rigid link, we will have elongation in these 2 links, and we have contraction in these 2 links. But the amount of deformation, elongation and contraction, they should be equal in vertical direction. So delta 1 in vertical direction is equal to delta 2 in vertical direction. That is equal to delta 3 in vertical direction. That is equal to delta 4 in vertical direction. This means if I assume each one as one spring, these springs, they are in parallel. So let's see what is the stiffness of each one. If I have inclined rod, I proved with this before. If I have inclined rod, Young one says it is E, cross-sectional area, it is A. the length it is L, I apply load P here, and the orientation of the rod and the load angle is alpha. In that case, the stiffness of this rod in this force direction, I proved this before, it is equal to EA over L cosine squared alpha. We know this. So this is the stiffness of this rod in force direction, and pay attention, this angle is alpha. So I know that. Now I will use this formula. So here, the stiffness for these K1 and K2, these two links, they should be equal, these two rods, in vertical direction. Pay attention, what is the alpha? Deformation, it is in vertical direction, so this angle will be alpha. So it will be EA divided by length. Length for this, if this is A and this is A, so A, the length, this length will be the square root of A squared plus A squared, so it will be A square root of 2, so EA divided by length L times cosine square of this angle. Because this is A, this angle will be 45 degree, so cosine square of 45 degree. In similar way, K3 is equal to K4, that is equal to E Young modulus times A cross-sectional area divided by length. Length for this rod, this is 2A, this is A, so in this triangle will be square root of 2A squared, it means 4A squared plus A squared times cosine squared of which angle? This angle. Here, if this is alpha 1, this is alpha 2. So what is the cosine of alpha 2? Cosine of alpha 2 will be, let's say right here, cosine squared of cosine of alpha 2, it will be 2A divided by, again, the length. Length from here we see it is square root of 4A squared plus A squared squared. So from here, this will be A square root of 5 times 2A divided by A square root of 5 squared. So what is the total now? Deformation for this rigid link in vertical direction will be total load P divided by equivalent stiffness. Equivalent stiffness here, it will be 2K1 plus 2K3, because these are equal, or I can write, let's say write like this. This summation of all stiffness K1 plus K2 plus K3 plus K4, because these springs, they are parallel. So this will be P divided by 2 A square root of 2 cosine 45 square root of 2 over 2 squared plus 2 A square root of 5 times cosine squared alpha 2 A square root of 5 to the power of 2. This will be the deformation of this rigid link in vertical direction. Next problem. Next problem, we have 4 rods. So we have 4 rods. And each one, let's say, right, what is E, what is A, what is L. This one it is L, E, A. This one is L, E, 2A. This one it is L, E, 4A. This one it is L, E, 2A. And point A, B, C, D. And this is point O. This system is subjected to one concentrated load at point O, and the orientation of this load with horizontal direction makes angle of alpha. So this angle is alpha. So external load P is applied at point O. Determine the angle alpha so that internal force in member OA, which means this member, is equal to half of internal force in member OB. I want to find this alpha so that internal force in this member is equal to half of internal force in this member. So how I can find it? Let's say decompose this force in 2 directions, in horizontal direction and vertical direction. If I do that, in horizontal direction, this load will be P cosine alpha. In vertical direction, it will be P sine alpha. So, if I put name for these, of course we have a name, I don't need to do that. So, here KOA is equal to, in the rod direction, in the horizontal direction, is equal to 2EA over L. KOC is equal to 4EA over L in the rod direction. So in the horizontal direction we have 2 stiffness, and the formation of each spring or each rod OA and OC should be equal in horizontal direction. Once I apply this load in horizontal direction, it means P cosine alpha. We have elongation delta in OA, and we have contraction equal to the delta again in OC. So I can write delta O in horizontal direction is equal to force in horizontal direction, P cosine alpha, divided by total stiffness in horizontal direction, because the formation is equal, they are in parallel, so equivalent stiffness is equal to summation of these 2. So from here I can find delta O in horizontal direction. It will be equal to P cosine alpha. This will be 6EA over L. In similar way, in vertical direction, delta O in vertical direction, total force in vertical direction is P sine alpha, and effective stiffness in vertical direction is the stiffness of OB and OD, and you see the stiffness of OB is equal to 2EA over L, and the stiffness of OD is equal to EA over L. So if I add together, I will have 2EA over L plus EA over L. This means vertical deformation is equal to P sine alpha divided by total stiffness 3 EA over L. Now, what is the internal force in member OA? Internal force in member OA is equal to stiffness of member OA times deformation in horizontal direction, that is P cosine alpha divided by 6 EA over L. What is the internal force in member OB? Internal force in member OB is equal to the stiffness of member OB, which is 2EA over L, times deformation in vertical direction, which is P sine alpha divided by 3EA over L. Now I should put these here. OA is equal to 1 over 2 OB. If you plug there EA from both sides, they will cancel, L will cancel, and P will cancel, and you will have one equation in terms of sine and cosine alpha, and you can find that alpha angle. Okay, let's look at the next problem. Next problem, we have 3 rods. EAL, EAL, EAL. We have 3 rods, and these angles should be 120 degrees. So in the following structure, temperature changes in 2 members. In 2 members, for example, member 1 and 2, temperature changes in 2 members is equal to delta T. We increase the temperature delta T from ambient temperature. We increase delta T, the temperature. Determine the internal force in each member. We want to find the internal force in each member. If we didn't have this member, what we'll have? If we increase, for example, temperature in member 1 and 2, and we don't have the third member, what will happen? In that case, we will have elongation in each rod, and the magnitude of that elongation, we know that it is equal to alpha delta T L, alpha delta T L. So if we increase temperature in each rod, delta T, so each one will expand, and the amount of deformation, the magnitude, it will be alpha delta T L. So if this is point O will transfer to the point O1. Pay attention, in the direction of the rod, elongation is alpha delta TL. In the direction of this rod number 2, again the formation is alpha delta TL. Initial length was L. Now our new length is L plus alpha delta TL, and in rod 1 again initial length was L, new length it will be L plus alpha delta TL. So point O will move down. How much will move down? In order to find that, to the center of this point, for example, if I put name A, B, C, for the center of A and the radius of L plus alpha delta TL means this length, we should draw one arc. Because we are in a small deformation range, that arc will behave like perpendicular to this direction. We should do similar things for this side, B. So our new length it is L plus alpha delta TL. So this rod new length it is L plus alpha delta TL. So to the center of B and the radius of L plus alpha delta TL means this length, we should draw another arc like this. Again in small deformation range, that arc will be perpendicular to that rod direction. So in order to find delta O1, it means this length, if this angle is alpha, this angle will be alpha. Look at to the shape here. This is perpendicular. This is alpha delta TL. This is O. This is O1. This height it is delta O1, and this angle is alpha. So delta O1, it means this cosine alpha should be equal to alpha delta TL. From here I can write delta O1 is equal to alpha delta TL divided by cosine alpha. So if we don't have the third member and we increase temperature in these two rods, point O will transfer down, and the magnitude of that it will be alpha delta TL divided by cosine alpha. Alpha here it is 60 degrees. So point O will transfer to point O1 and it will be alpha delta TL divided by cosine 60. Because in reality we have third member, so if point O will move to point O1, this rod will react against that and it will apply external force such as F. So now this is point O1 and this is upper side of our structure. This is the reaction internal force in this member. F applies upward and it wants to bring it back. So point O1 will transfer to another point like O2. So total deformation will be delta O1 minus delta O1 O2. This one is equal to deformation of point O. Now delta O1 I calculated. If internal force inside of this member it is F, because if of this external force, how much point O1 will move up? We can calculate that because we know E, A, L for this member, we know E, A, L for this member, and they will deform in vertical direction both equal, so both of them, they are in parallel, and the stiffness of each one is equal to E, A over L cosine square of this angle alpha, which is 60. So this delta will be F force divided by total stiffness. We have two rods. It will be 2EA over L cosine square alpha. So it will move up minus F divided by 2EA over L cosine square 60. Finally, that will be equal to final deformation of point O. Final deformation of the point O will be internal force in this member divided by stiffness of this member. So it will be equal to, if I assume internal force in this member, it is F. Deformation in this member will be F divided by axial stiffness, F divided by EA over L. From here, we have one equation, one unknown, so we can transfer this term to other side, and we can write F L over EA plus F L divided by 2EA cosine square 60 is equal to alpha delta T L cosine 60. This is one equation, one unknown. I can factor out F. So from here I can find F. Next problem. Next problem. We have one rigid beam or column, rigid column for example. We attach this rigid column using 4 rods to the support. And we have one in support here. So rod number 1, number 2, 3, 4. These space in vertical direction, they are equal, each one it is W. This is E1, A1, L1. Again, this is E1, A1, L1. This is E2, A2, L2. And again, this is E2, A2, L2. So 2 by 2, material property and cross-sectional, they are equal. In these two rods, the Young-Montes, it is E1. The cross-sectional area, it is A1, length L1. In these two rods, the cross-sectional area, it is A2, Young modulus E2, length L2. And we have this system. And you see, this is spacing in vertical direction, it is W. We increase temperature in rod number 1 and 4. In rod number 1 and 4, we increase temperature. We increase temperature delta T So we increase temperature, delta T. We want to find internal force in these bars after increasing the temperature. So, if we increase the temperature in these two rods, what will happen? This will rotate. So, this rigid column will rotate respect to point O, and we have this shape. Okay, will rotate. So, let's see how we can calculate internal force in these members. It is easy if we use superposition here. If we have rod only 1 and 4, what will happen? If we have rod 1 and 4, and we increase the temperature, this will rotate, and there is no internal force in any member, and these delta will be alpha delta T L1, alpha delta T L1. So freely it will rotate this rigid link, and each one expand as much as alpha delta T L1, and there is no internal force. But in reality we have these two members. If the rod number 1 and 4 expand alpha delta T L1, in that case here and here we have deformation, and we can find deformation. How much is that deformation? From similar triangle we can find that if this deformation in the horizontal direction, I assume magnitude is x, x divided by alpha delta T L1 is equal to W, because from here to here it is W, divided by 2W. So from here we can find, from similar triangle, x is equal to alpha delta T L1 over 2, and again here it is alpha delta T L1 over 2. Okay. Once we have these two members, member 2 and 3, these elongation will force inside of these members. How much force it will produce in these members? They should be equal because the deformation is equal, but they should be equal in opposite direction. This will be F in this direction, for example. This will be F in this direction because it wants to return to the initial position. So it should push from right to left, it should push from left to right, because they wanna return to the initial position. The magnitude, this is F, I assume. They should be equal, but I don't know the magnitude of F. If now I apply F force here, F force here, what will happen? These F force here, they will produce how much force in these rods? Here I have F, here I have F, here I have rod number 1, here I have rod number 4. It is clear, force inside of this you can find from equilibrium equation. This will be F over 2, and again this will be F over 2. So now, once we don't have these members, for example, if I put this point name, it is O. Look at to deformation. O will transfer to the O1. So delta O1 from left to right. That deformation will produce internal force, reaction force in this member. That reaction force, for example, is F. F will push it back. So F will produce deformation in inverse direction. This, for example, now location is O1, it push it back to the O2. So minus delta O1, O2 from right to left should be equal to resultant deformation of point O. Now, look at to this equation. Delta O1, because of this expansion, is known. I calculated if we don't have this rod, it is alpha. Delta T L 1 divided by 2 minus, if this rods here, rod number 2 and 3, force inside, it is F, so deformation will be, because this is F, this will be F over 2, so if F over 2 you apply in this rod, deformation will be internal force divided by the stiffness of this member, which is E1, A1 divided by L1. So this point, the deformation in rod number 1 will be F over 2, E1, A1 over L1. But deformation of O1, O2 from similar triangle will be half of that. So it will be F over 2, E1, A1, L1 times half. So this rod will deform as much as internal force divided by stiffness. But from similar triangle, if in this rod we have this deformation, in rod number 2 deformation will be half of that. So it will be F over 2 E1 A1 over L1 times half. That is equal to final deformation in this rod. Final deformation in rod number 2, it is equal to force in rod number 2, which is F, divided by stiffness of that rod, E2, A2 over L2. From here, you have one equation, one unknown F, so you can take this term to other side and you can find internal force in this member. Internal force in this member will be F. In this member, because of symmetry, will be F. In these two members will be F over 2. Okay, next problem. Next problem, we have one rigid beam and one inclined rod. This is E, A, and the length for this you can find, assume it is L. From here to here it is 0.6 meter. From here to here it is 0.2 meter. This is angle theta, for example, it is 40 degrees. And this beam is subjected to uniform distributed load, and the intensity of this load, for example, it is W kilonewton per meter. Let's I show this given with parameter like this will be L1, this will be L2, this is theta. So we have this rigid beam. This rigid beam is subjected to uniform distributed load. The intensity of load, it is W kilonewton per meter. From here to here, from point B to C, it is L1. From C to D, it is L2. This angle is theta and this is EAL. We want to find delta D. So this is rigid beam. If we apply load, what will happen? We will have elongation in this rod, for example AC, and this rigid beam will rotate. This point C will transfer to point C prime, and point D will transfer to point D prime. We want to find DD prime. We want to find deflection at point D. How we can find it? It is easy. If we cut this and find the F force here, to see how much force we have in vertical direction because of this distributed load, I can find that summation of moment respect to point B is equal to 0. So F, because I am finding this F and this F, it is in vertical direction, I will show Fv times L1, okay, minus W times L1 plus L2 times L1 plus L2 over 2 is equal to 0. So I'm taking moment respect to point B, Fv times L1 minus W times L1 plus L2. This will be resultant force. Where is the resultant force location? The middle of rigid beam. So L1 plus L2 over 2 is equal to 0. From here, I can find F vertical. If I find F vertical, so this rod will subject it to F vertical at point C. If this angle is theta, this angle is alpha, and alpha we can calculate it. It is 90 minus theta, so I have alpha. And the length for this is L. Because I have this length L1, I can find L in terms of L1. Because L cosine theta is equal to L1. From here I can find L is equal to L1 divided by cosine theta. So stiffness of this rod in the force direction will be EA divided by L, which is L1 cosine theta, times cosine is square of this angle, cosine is square of angle 90 minus theta. This will be stiffness of this rod in vertical direction or in force direction. So CC prime delta CC prime will be FV, which we have it, divided by KV. If we find delta CC prime from similar triangle, we can find delta D, because delta C divided by delta D is equal to L1 divided by L1 plus L2 from similar triangle. If this is delta C, which I find it, this is delta C, force divided by stiffness, over delta D, which problem statement asks, it is unknown, is equal to L1 divided by L1 plus L2. Okay, I think it is enough for today. Thank you so much for watching this lecture. See you next session. Bye.